Okay, so today I'm going to talk a little about propellers and propeller testing, but before I did, this is a quick and dirty example of a tethered electric airplane. It's got some styrofoam, it's got an airfoil cut into the wing using a hot wire cutter, it's got a battery clip so that power can come from the tether pole, comes out down underneath the wing right here, and tucks into the fuselage, comes out to the motor right here. The motor's supported by some landing gear, and it's all held together by elastic bands, at least until you get to the point where you know everything's balanced and flying. Now, key thing to keep in mind is that the propeller we're dealing with has to mount onto that motor shaft right there, okay, which does put some limitations on things, such as the size of your propeller, okay? You can see this one right here. When you go to take off, this propeller is going to be physically too large for this landing gear on this airplane. You also can't whack into your landing gear. In fact, propeller size was one of the issues for fighters in World War II. And if you look at something like the Corsair, you'll notice that it's got its classic gull wings so that the landing gear can come down a little bit lower so they can put a bigger propeller on it. Anyways, let's take a look at some of the classic choices for propellers and how to make a decent prop. So right in here, we've got one of our original style propellers. Okay, and the original style propellers that we made when we started this project, they were made just with a piece of dowel and then 2-liter plastic pop bottle. We would take the large cylindrical section, lay it flat, and then cut these propeller blades at an angle along there so that they'd have some natural curvature to them. You can see there's a little bit of a curve there. That's a gentle curve, is because it came out of a 2-liter plastic pop bottle. And anyways, you would drill a hole right down the middle of the dowel, and then that could be just press fit right onto the propeller shaft. And these actually worked really well, and we had students who really got into it and made multi-blade prop designs. And the catch is the epoxy that we used on the prop blade joint in there. You did have to let that sit overnight for it to cure. So students, before their flying test day, needed to have a few of them made up, and consistency was a little bit challenging to come by. Now, I've had students at BCIT who've had success with this technique. You can see there they marked the center for their dowel. I'm not quite sure why they didn't just take it down, put it on a machine lathe, and drill it out. If you're doing this in a shop that doesn't have lathes in it, I'm sure you can come up with some kind of jig for drilling that on a drill press, or an appropriate way to make sure that you get nice center holes on all of your dowels. This one, exposed hot glue, one of my least favorite things in the shop. But in this case, it held together. And then I'm not quite sure about the tape. I think they laid the tape on over top so that they would have additional adhesion to the hot glue, because plastic doesn't stick really well to hot glue, but the tape did stick well to hot glue, and the tape also stuck well to the propeller blade. So a couple of interesting designs right in there. And we've got a few other designs based on that. Here's one you can see that the hole doesn't go all the way through. It's still a press fit propeller that's just going to press right on here. But because they didn't run the hole all the way through, they could use a single piece of plastic. And here, rather than using pop bottle plastic, which is admittedly pretty thin, they went down to the plastics lab, and I think this is about 1/32 or about 30 thou thick plastic that they actually thermoformed. They heated it up and gave it a little bit of twist on its own, and you might not see it on that one, but which one has it? Anyway, I think there's a screw sitting right there underneath the tape. And here's one that maybe shows it a little bit better. I'm not sure what they were using here. It looks like some of the PET-G, in fact, that we use for the propeller blade safety shield. And there they actually sunk a screw down to help hold that in place. And again, this is just a press fit right onto the propeller shaft. And you can actually start getting some fairly fancy designs if you take the time and think it out. And in fact, you could probably throw the PETG onto the laser cutter, cut out your template, and then thermoform it into shape. So a couple of neat ways to make propeller blades that way. And the great thing about the press fit style is that it's easy to put on, easy to take off, it's quick, it's simple. It does work quite well, so long as you keep your propeller blade fairly small. If your propeller blade starts to get too long, or you've got too many blades on there, all of a sudden you start to get a high torque load on there, and now you've only got this small distance right in here to deliver that torque load. So small distance in here, large distance out here that you're delivering it to, that's that's just asking to have something slip in here at the center. Now, some of my students were having that as a problem, and so the motor would start spinning, the prop would really be biting the air, it would have a lot of load on it, this would spin inside the dowel, and the prop would come flying off. And the prop would merrily go out, keep flying across the classroom, while the plane would drift into a smooth landing. It wasn't really a problem because you could just go and put the prop blade back on. And sometimes what they'd have to do if it got too worn out is they'd slide a little super thin piece of wire down inside there just to thicken up the hole a little bit again and give it a little bit more purchase onto the motor shaft. However, I've got enterprising students here at BCIT, and they come up with some interesting other solutions, and they wanted to go and start making bigger props and using different styles. And so they came up with this idea right here. And again, this goes a lot easier when you've got access to machine tools and know how to use them. But that's one of the neat things about what we do here is it's a multidisciplinary program. And let me just zoom in on that so you can see what they've done. Refocus there, please, camera. Okay, there we go. Right in here, you can see that they've just taken, in this case, a 1/4 inch bolt, and I'd suggest using a fine thread, but they've taken the 1/4 inch bolt and they've center drilled it and drilled out a hole in the middle, again, so they can press fit this on here. And now you can take a propeller, mount it on right there, and that one, zoom out a little bit, maybe that'll focus a bit better. That one needs a slightly longer bolt, I guess, but you can take a propeller blade and you can mount it on there, and then you can screw it down into place. And if you do your screw up nice and tight, then you've got a really solid press fit. Now, if you're going to do something like that, remember when you go to press fit that motor, press fit that bolt onto the motor, that you're going to need to use the arbor press or something like that. And down at the bottom of your motor, it is a little bit sensitive right here. If you're using the arbor press, make sure you get in there and you support the shaft. Don't rest the motor on the bearings right here because you'll put too much force on a little motor. You need to be pressing on the shaft because up at this side, you're also pressing down on the shaft. So that allowed them to get into making some 3D printed props. Now, 3D printed props seem like a good idea, and there's a program called OpenSCAD that if you go on Thingiverse, you'll find that one of the users on Thingiverse has a multi-blade parametric propeller generator, which is how these props were generated right here. There are some problems with support material. So as you know, if you've done some 3D printing in the past, when you print, the top side comes out okay because that's where the nozzle is, but all of this stuff underneath right here needs to be supported. So if you flip that over, this one came out pretty ugly on the back. Your printer needs to be able to handle support material if it's going to do anything too fancy on there. And there's another one that came from the OpenSCAD propeller generator, but quick way to create these. Now, the downside is, of course, when you print in PLA in particular, and in fact, most of our 3D printing printed materials tend to be a little bit brittle. So if you're flying these flying them in particular, we've got safety shields and we're testing. But when you're flying with 3D printed propellers, it's pretty imperative that everybody in the room, anywhere near them, have proper eye protection. And anybody who's within about 10 feet probably should have a face shield on over top of that as well. Now there's some other neat designs, as you can see. Very classic carved wood propeller. No reason you can't do that. This one worked just fine. And in fact, wooden propellers are still pretty commonly used on airplanes. You can also go the store-bought route. And so this is designed for radio control electric airplanes. And you'll notice on the sides of some of these that they'll have a number. This one says EP, which probably indicates it's for an electric plane. Okay, they have different propellers for electric planes, and then you'll see it's 80-60. So standard, that would be an 8-inch propeller with a 6-inch pitch. What do I mean by that? Well, those are pretty standard propeller terms. 8 inches from tip to tip. Now, as we saw earlier on our plane, that's going to be a real issue unless you build the landing gear up bigger or something like that. It can also be a problem for your motor because long propellers require more torque in order to turn them around. And that becomes an issue of getting the torque out to the propeller. As I was saying, you can sometimes have slippage between the shaft and the prop, but it also becomes a problem because torque requires current, and the more current you draw through the motor, that's the harder it is on your power supply. Your power supply is going to be limited on current, so if it's too long, then your propeller's probably not going to be that super efficient, not going to have benefits from going that long. Now, the pitch is a term that also applies to all propellers, and you can see that looking at the leading edge of the blade back to the trailing edge, that there's a bit of an airfoil on there, and in fact it's a very intentional airfoil with some nice curvature that doesn't really show up well in the camera, but take a look at some commercially made propellers, and the pitch is just like the pitch on a screw. If it's a 6-inch pitch, that means that as the propeller completes one revolution, it should move 6 inches forward through the air. Now, a 6-inch prop actually for what we're doing makes a lot of sense, but if your pitch is too steep, then you're going to end up stalling the propeller, and you're just going to end up moving air around in a circle rather than pushing it forward. And you can think about that when you're driving down the road in a car. If you stick your hand out of the car window, hey, there's a window. We're driving down the road, there's a car. We're driving down the road and you stick your hand out the car window, and if you're perfectly flat, okay, well, then you're getting drag, but you're not getting any lift. And then if you change your angle of attack a little bit, and now you're hitting the wind and you're pushing air downwards, that's going to push your hand upwards and start generating some lift. Okay, so somewhere in that range of angle of attack, then you're going to have some lift being generated. Or in the case of a propeller, that would be in the case of a low pitch to a medium pitch, you're going to have some thrust being generated. But if you turn your hand too far, well, now you're not generating lift anymore because basically your hand is almost at 90 degrees to the oncoming airflow, and you're just getting drag. It's pushing your hand back over here rather than lifting it up. So your wings won't generate lift if they've got too steep an angle of attack, and your propeller won't generate thrust if its pitch is too steep. Now, one of the things that you'll find that real airplanes have is variable pitch. So when they're taking off, they can keep a fairly low pitch so they grab air and pull it quite easily. But when they're up in the air, they can steepen their pitch because now the airplane is moving forward through the air, and so air is flowing over the propeller, and it can bite in, and you can have a much steeper pitch when you're flying at altitude for a whole number of reasons, but mostly you're moving forward. When you're down at the ground and you're just starting out, you want a fairly shallow pitch. We're going to be working with a fixed blade or a fixed pitch propeller, so you don't get to play around with all of those parameters. Let's see, other things with store-bought propellers. This is a fairly standard style of store-bought propeller, and you can see it's got a super steep pitch on it. Okay, now this is no good for the motors that we're using. Our motors spin too fast. If you look on there somewhere amongst the shattered remnants of the hub, this was designed for flying on those little elastic band powered gliders. And of course, being powered by an elastic band, you're going to have a bunch of torque coming to there, okay? But you're not going to have a lot of speed, not a lot of RPMs. So a steep pitch kind of makes sense because you can grab air and you can twist through it and you'll move forward. Whereas with our prop, which is going to be spinning super fast, like thousands of RPM, this prop is just going to be in stall. Oh, and while we're at it, you can see that tiny little hub on there, even though someone tried drilling it out to make it fit, just really was not a good fit for going on to our motors. I did try ordering some of these nice little propellers. I'm not 100% sure if they weren't designed to be used underwater. And it really does look to me like they're a pusher style design. You can kind of feel that if you take a look at the blade and look at the curvature on the blade and say, well, what's that airfoil doing? And again, let me see if I can get it. Now you can see there's a little bit of a curvature right in there, and I'm just looking at that, and it doesn't really make sense to me that we'd want the concave side. So right now, I need another finger here while I'm holding this. You can see the concave side is right in here where my thumb is, okay? And the convex side is over on this side. You don't want, if I was spinning that way, then I'd be pushing with the convex side, which, I mean, it'll work. But usually when you look at airfoils, when they're grabbing air, you want the concave side to be grabbing there. So I think this prop looks like it's really designed to be used in a pusher type application and to spin around this way, grabbing that air into the curve of that blade, and then once it grabs it, making it go steeper and accelerating it backwards. Okay, so for using something like this, the hub is a little bit small anyway, so it's probably going to have to be drilled out to size. You may as well drill it all the way through. And if I was going to use this one, I'd probably try mounting that on the airplane this way around. I mean, go ahead and try it, put it on that way, and spin it around, see how it goes. But I think I might try drilling that all the way through, putting it on there like so, and spinning it that way. Alrighty. So there's some things to look at in terms of your prop design. Now, in the event, I said that you want your motor to spin this way or that way. In the event your motor's spinning in the wrong direction, of course, just come over to your power supply and unplug and replug your leads in. That'll reverse the polarity of the motor and reverse the direction that it spins. For testing your propellers, we're going to put them inside a safety shield right here so that people don't go sticking their fingers in there, or so that if something goes drastically wrong and the prop shatters, the blades don't go flying all over the place. Now, the ideal way to test your propeller is with the blades pushing air upwards. So here you can see that curvature of the blade is going to grab the air and it's going to push it upwards so that your thrust is going downwards. And that way your thrust is coming right down here into the scale, and you can measure the thrust on the scale. Now, if that's not going to work for you, we do use a big block of wood on here to put some weight onto the base so that we'll actually be able to read it as a negative thrust. But anyway, I've got little holes in the safety shield down here, well, large holes in the safety shield down at the bottom, not only to allow air in, but allow my finger to reach in here and to turn the scale on. And as you can see, it starts out and it tears the scale out at 0, even though it's already got a big weight on it. Over here on my power supply, I've got the wires connected right into here, and I've got my power supply voltage turned all the way down. and my current turned all the way up. Now that doesn't mean that is current flowing right now, it just means that I've got my full current available. Okay, so I'm going to be able to turn up my main voltage. You got fine voltage right here. Make sure that's turned all the way down, and you can probably hear the propeller spinning right over here. Now this is a time where you want to stop and just watch and make sure that your propeller's spinning okay and that it's not vibrating a lot. And you can see right down on here that I've got 7 grams of thrust already. And as I increase the voltage, I start to get more and more thrust. I think as we pick up the speed, you can start to appreciate why we've got the safety shield around there. So now I'm at 69 grams of thrust, and 75, 76, 78 grams of thrust. So that's probably enough to keep the airplane up in the air. And if you come over here and take a look at your power supply, that's at 7.8 volts and 680 milliamps. The motor's probably pretty happy running like that, but we're not. So let's take it up right here. And you can hear that's really coming along, and we're getting, so that's up at about 20 volts right now, and we're generating 152 grams of thrust. And now I've maxed out on my power supply, and we're generating 180 grams of thrust. And if I come back over here and look at my power supply, you'll see that I've got 25 volts. Now this power supply can supply more than 25 volts. But what was happening was I think I was hitting my maximum current limits. So I was up at, let's just run it right back up here. I may have been hitting my maximum current limit right there because I think my power supplies are supposed to go up to 30. Now some I've got that are 24 volt max power supplies, and some are 3 amp current limits. This one I thought was a 5 amp current limit and a 30 volt maximum. But in any case, sometimes if your prop is too draggy and is creating too much drag, or basically too much torque for the motor to spin, you're going to hit your current limit before you hit your voltage limit. And if your prop isn't aggressive enough, then you're going to hit your voltage limit before you hit your current limit. Now remember that current times voltage is power. P equals VI. Okay, so when you multiply these two, you get your power that's available for the motor to use. Now, is it using it all efficiently? Oh, heck no. But on here you can see at 325 volts and 3.3 amps, that's 75 plus, somewhere in the low 80 watts available. And we should be able to get up to 100 watts or more if we balance that out correctly. Anyway, that's one propeller test right there. It was 180 grams, and you'd record that at 3.3 volts and 25 watts. That was where you came to the end. Now, you don't want to run your motors at 3 amps for a long period of time. Let me just turn the power supply off here, and usually I'll unplug one of the connectors just so nobody accidentally bumps it and turns it on for me or anything like that while the safety shield's not in place. You don't want to run that for too long at those kind of currents, because if you come in here and touch your motor, you'll feel your motor getting warm. And that's one of the downsides of running with a very large or very heavy thrust prop. Okay, it's great for getting you up in the air, but as soon as you're up in the air, you got to dial that power back. Otherwise, you're going to start overheating these motors. These motors were not designed to run at the amount of power that we run through them on takeoff. They can do it briefly, but if you keep doing it, you're going to burn that motor out, and then you have to take your airplane apart and rebuild the whole motor or replace the whole motor. And well, that's kind of what happens in any sort of vehicle when you run the motors too hard. So I switched over to the other testing jig now, and we've got a 3-bladed thermoform prop on here. Let's take a look in here at that without, oh, there we go, too close. I guess we're out of focus a bit there. Anyway, let's take a look down here. We've got the scale Tethered. It's showing 0 grams. Now this prop, the way it works, is not going to work particularly well as a pusher. So we've got it set up in a pull configuration. We want it to come around this side, and you can see that it's going to grab the air. It's going to force the air downwards. That's not as great because as soon as the air goes down there, the air is going to hit the base, and that's going to affect your measurements a little bit. Oh, this one likes to turn off easily. Just keep an eye on that and keep it powered up. And let's give that some voltage and see what starts to happen as that flies. Oh, now down here it's showing me 0.2 ounces. Set that over to grams. Woohoo! 5 grams of thrust. Now, don't put your face over there, but put your hand over top, and I can't feel too much air movement coming out right there. When you've got a prop blade that's working really well, you're going to expect to feel some air movement, and that one is just giving us 5 grams. But you'll notice over here, when I crank this up, I guess 25 volts is my limit. This one's drawing 2 amps right here, and the main thing it seems to be doing is generating noise and vibration. Now, that's probably got more to do with this specific prop than anything. You'll notice it's a little bit wonky on how it was put together, and maybe that's why a student left it behind for me. Also, it's possible that maybe I was spinning it in the wrong direction. It's kind of hard to tell once they start moving. So the beautiful thing about DC electric motors, you just reverse the polarity of the motor. Oh, now that's looking a little better. So now, sounds quite a bit different. And down here, you can see I've got negative 33 grams. Well, it shows me negative 33 because I had that big weight of the base on there. So when it was showing 0, it was actually reading a few hundred grams because of the base. All right, let's crank this up. We're at 18. 25. Oh, and now this can only read so far into the negative. So it's only giving me numbers down to negative 36, and then it goes off the scale. Okay, so I'm going to have to make a few changes so that I can read this. Hold on. I've now added a 500 gram weight to the base, and we're showing 502 grams. I'm not going to tear it this time. Let's crank this up. And we're up to 25 volts and 2 amps. And now I'm down to 445 grams on there. So that one's generating over 50 grams of thrust, because when I take that away, I come back to my 501. Now, I think this one is actually generating more than that. It's just really hard to test because in this configuration, all the air is coming downwards inside here, and it's hitting right here, and then it has to get out through these holes at the bottom. It's a lot easier if you can suck the air in and then blow it out the top, because there's a lot more space for that high velocity air to go right up there. Okay, so it's just a little thing about testing. Our testing jigs are far from perfect testing. Aerodynamics experts would tell you that having this ring around here probably causes an interference with the tip vortex. And of course, this is what we call a static thrust test. The interaction of your propeller with the air as your propeller moves through the air is going to be different, because as the plane is flying through the air, the air velocity coming over top of it is much higher than it is sitting right here. Right here, the air velocity is 0. So that was 2 different props. Let's take a look at one more. Okay, here's another homemade prop. This is hot glued in place, with a little help from the tape, and the plastic has been twisted here, but made using the classic technique of using a hacksaw to cut a small groove at an angle representative of the pitch into the edge of the dowel, and therefore that blade's going to be able to spin around. Now this one, it's got a nice feature that it's been drilled all the way through right here, so that this can be mounted either in a pusher or a puller configuration. And this one I've been able to set up so that as it spins around this way, it's pushing air up that way. Let's see how this one does. We've teared the scale. We're starting at 0, and now I can feel airflow coming up right over there. Again, use your hand, not your head, to feel the airflow. I'm showing 30 grams down here, and I'm only at 9 volts now. You can see we've got a bit of vibration in there, and that's causing our base to start to move. And this one maxes out at about 90 grams, and whoa, look at that, 4 amps of current. That motor was really working in there, and probably deserves a chance to cool down for a little bit. Now, the other thing you'll notice about this one is super steep pitch on there, okay? I bet if that prop had a lower pitch, you can see how that's almost a 45 degree, actually that might be more than a 45 degree angle in there. That's really hitting the air hard, and it's not kind of grabbing it and gently convincing it to go upwards. You're creating a lot of drag on there. And so maybe not the most efficient propeller design. There's lots of tricks that have gone into building propellers. And if you do your research on them and take a look at airfoils and pitches and how they all come together, then you're probably going to be at an edge over people that just go out there and start randomly sticking things together. But here's an idea. This is to show you a couple of ways that you can test your different propellers. Oh, one more thing before I go. I guess you're all wondering how that store-bought propeller was going to perform. So I had to drill it out to get it to fit onto the 1/4 inch shaft here. So I need to make the hole in the hub a little bit larger. And let's see, I want the airflow to be coming upwards off of this one. And just looking at the curvature on there, and I think that's the direction that it's designed to go, to come in there. Yeah, it's going to grab that air. You'll notice they do this little thing where at the inside, okay, towards the hub, there's more meat to the propeller, and it's at a more aggressive angle, and it flattens out as it comes out towards the tip. Now, when you think about it, what's happening is that the tip of the propeller is rotating through a much larger volume of air, okay? So in order for the inside right here to pick up an equal amount of air and to push at the same rate as the outside, you need that little twist to the blade and that little change to the airfoil shape. That was part of the reason why we're using the sides of 2-liter plastic pop bottles, is to get a little bit of curvature into the blade. But anyways, I'm gonna zero my scale here, and there we go, 0 grams. Let's see right here, helps if I plug it in, make sure it's spinning the right way. Okay, hard to see on video which way it's spinning, but let that get going there, and I can feel the air moving up at the top. Just put your hand out over top, and there it's moving up right on there. I'm at 3.3 volts. It's already up to 10 grams. Let's see, 64 grams at 8 volts and 1.2 amps. over here at 25 and 4.4. I'm flying on there, and that's giving me 171 grams. Woo! Now, I think that prop can be improved. I noticed that it was running all the way up to 4.4 amps, and your motor's not going to last long at 4.4 amps. So if you want that kind of rotational speed from your motor, what I'd take a look on here is, you notice how long those blades are. I'd consider cutting maybe a couple of centimeters off the end of each blade, and that would enable the prop to spin at higher revolutions. It would probably spin a little bit faster at a little lower current, and that might allow you to sustain those sorts of speeds, because like I say, 4 amps is going to burn your motor out very quickly. Not only that, you're going to have a problem fitting that onto the nose of your airplane without some massive landing gear, and that massive landing gear is going to end up creating more drag on your airplane. So anyways, depends what you're looking for in your propeller, but there's all sorts of design challenges that you've got in putting this together. Think about props, test the props, try a few different styles, build them, test them, build them, break them, make them better next time, and have a good time with step 1 of the Tethered Electric Airplane project. You will not get into the air until you have a propeller. So the the testing jig is pretty easy to make. You need a scale, just a standard kitchen scale will do the trick. About 15 bucks if you catch them on sale at Canadian Tire. A lump of scrap wood. Now this has a bit of mass to it, and then you're just going to take a 1/2 inch dowel. Now before you throw the dowel in there, cut a little platform in here. This is where the motor is going to go. Sits right up on there. We'll hold that in with some zap ties and a hose clamp. Probably a better way for mounting the motors to actually use the 2 little screw holes that are mounted right on here, and you could just mount that and screw it right into a piece of sheet metal or something like that. That would hold it really nice. But anyway, we're going to hose clamp it on, and then we're going to use some 2-sided tape to stick the base onto the scale. So there we go. That's about all there is to it. And there we go. Easy peasy testing jig. We've got the prop quite secure in there because of the hose clamp. When you get the longer props on there, you'll be surprised how much torque goes on there and tries to twist it out. We've got the base that provides a little bit of mass to help keep things from vibrating. 2-sided foam tape stuck down onto the scale. And there we go. Cables that come back to the power supply. And of course we need a safety shield to go around it. And that's just a piece of lightweight PET G in this case. I think it's 30 thou thickness or something like that. You could use polycarb 1/16 inch Lexan or something like that too. And all I've done is I've punched a couple of holes in it right here. Hold it together with zap ties. When you're done doing the unit, you can undo the zap ties and store it nice and flat in your shop. That's a 4-foot circumference piece right there. So just chop a strip off of a 4x8 piece. Down at the bottom here, you can see I've used Whitney punch to punch some big holes in it. If you didn't have that, you could just use scissors to cut some V grooves or something like that. You could probably do something a bit fancier and have it stand up on dowels or whatever. This is multi-purpose. It lets air flow in here when your prop is blowing it all upwards, and it also lets you reach in here and tear your scale and do stuff like that. So there you go. Probably easier than trying to remind people to wear face shields. Just make sure they're not sticking their head down on the inside when they're operating it.